Welcome to the last lecture video for differential equations. Though it seems like we've covered a lot of ground this semester, we've only scratched the surface on solving differential equations and systems of differential equations. Beyond this class, there are also numerical methods for solving differential equations, and there's a lot of support from computer algebra systems in doing so. There's also a class of differential equations called partial differential equations that remain beyond the scope of this class. In section 5.5, we're going to progress from first-order systems to second-order systems, solving those with the eigenvalue method, and our mechanical applications to spring mass systems. Let's consider a second-order system through the lens of our mass spring system. Consider three masses connected by springs and fixed to a rigid wall. So let's draw a picture of our experiment. We're going to have two rigid walls and a surface upon which three masses will oscillate. So let's draw our three masses, mass m sub 1, mass m sub 2, and mass m sub 3. We're going to connect these three masses with springs. Each spring has a spring constant. Let's name them k sub 1, k sub 2, k sub 3, and k sub 4 respectively. This is going to be a model for free motion. That means we're going to have rigid fixed supports on either side. If we were to interfere with those supports and cause oscillation, we would have an external forcing function matrix. This will also be undamped motion. That means there will be no resistance to the velocity of those masses oscillating on the surface. So there won't be any dash pots or shock absorbers in this particular system. Our goal is to model the position of each mass at any instant in time within the oscillation of this system. So let's suppose that x sub 1 of t gives the position of mass 1 at any particular time, and the line that I've drawn here represents its equilibrium position. If this mass moves to the right, that's positive motion. If it moves to the left, that would be negative motion. So each of these three masses will have some sort of equilibrium position, modeled by x sub 1 of t, x sub 2 of t, and x sub 3 of t, respectively. The model for this system consists of Newton's second law, mass times acceleration, and Hooke's law, spring constant times displacement, x. So let's set up a system of three differential equations of second order. Looking at the position of our first mass, denoted by x sub 1, we're going to have mass sub 1 times acceleration x sub 1 double prime. This is going to be in the opposite direction of Hooke's law. So looking at spring k sub 1 acting upon mass m sub 1, we're going to multiply negative k sub 1 times x sub 1. Again, that's Hooke's law applied to the first mass. Now, not only acting upon mass m sub 1 is k sub 1, but also this spring with spring constant k sub 2. However, let's suppose that mass m sub 1 moves to the right a particular distance, and m sub 2 also moves to the right. Well, the spring constant, the net displacement for spring 2 would be the difference in those two displacements. So this would be plus k sub 2, spring constant from the second spring, times the net displacement of that second spring. So this represents the distance that spring 2 stretches. Okay, looking at the second equation for the second mass and applying Newton's second law, we have mass m sub 2 times position x sub 2 double prime. Applying Hooke's law here, we've got spring 2 with spring constant k sub 2 acting on one side of that second mass. So it's going to have term negative k sub 2 times x sub 2 minus x sub 1. On the right side, we have spring 3 acting on mass 2. The spring constant there is k sub 3, and the net displacement for spring sub 3 is going to be the difference x sub 3 minus x sub 2. This is the distance, the net displacement that spring 3 stretches. Finally, we've got one more equation, mass m sub 3 with displacement x sub 3. So there's mass times acceleration from Newton's second law. And we have spring constant negative k sub 3 times the net displacement of spring 3. But we also have spring 4 acting on mass 3. So we're going to end up with negative k sub 4 times x sub 3. As we did with first-order systems, we can express this system in matrix form. So here's what it's going to look like. We're going to start with a 3x3 mass matrix. So it's going to look like the masses times an identity matrix. The masses will be along the diagonals. And we'll have a 3x1 column vector of displacement vectors or displacement functions. So what we have on the left side here is the mass matrix. We're going to call this big M. This is the mass matrix. And right here we have x bar double prime, or the acceleration vector. Acceleration vector. This is going to be equal to what we're going to call the stiffness matrix, which programs in all of the spring constants, times the displacement vector x sub 1, x sub 2, and x sub 3. So this part is the displacement vector. Now, for our stiffness matrix, this one is the stiffness matrix. We're going to call this one K, and our displacement vector over here is x bar. So in column 1, I want to collect all of the terms from my system that are coefficients of x sub 1. So looking at equation number 1 and combining like terms, combining the coefficients of x sub 1, we would end up with something like negative k sub 1 plus k sub 2. The coefficient of x sub 2 in equation 1 is k sub 2, and notice there is no x sub 3 term in equation 1. Looking at now equation number 2 from our system and combining like terms for x sub 1, notice there's only one x sub 1 term in equation 2. Its coefficient would be k sub 2. Combining coefficients for x sub 2 in equation 2, we would end up with negative k sub 2 plus k sub 3. And for term x sub 3, we have one coefficient, k sub 3. Finally, looking at equation number 3 in our system, picking up coefficients of x sub 1, notice they are missing, so we'll put a placeholder of 0 in here. Coefficient of x sub 2 ends up being positive k sub 3. And finally, coefficients for x sub 3, when we combine them, would be negative k sub 3 plus k sub 4. Okay, so that is our mass matrix times the acceleration vector equal to stiffness matrix K, those coefficients come from your spring constants, times the displacement vector X. These two systems are identical. One is in equation form, the other is in matrix form. Now, writing it in matrix form makes it convenient to find the general solution to this system. So part 2, let's consider the solution to this second order system. For the second order system given by x double prime equals ax, assume a trial solution of the form x equals VE to the alpha t. Now, before we move on, there's one change here that I want you to notice. X double prime has been isolated from our original matrix equation. So let's see how that works. We started with mass matrix times X bar double prime equal to stiffness matrix K times displacement vector X. Now, we don't have a whole lot of experience with linear algebra, but you can probably understand that to solve for X double prime, we need an inverse. We're not going to divide both sides by matrix M because matrix division is not actually defined, but we're going to apply an inverse matrix to both sides. So applying M inverse to both sides, we end up with an isolated acceleration vector on the left, and on the right side we've got the product of two matrices, M inverse times K. We're just going to call that matrix A. So by isolating X double prime, we end up with a matrix equation of this form. It's really close to what we did with first order systems, but we have a second derivative as opposed to a first derivative. As we did with first order systems, we're going to assume a trial solution of the form X equals vector v, that's an eigenvector, times e to the alpha t. Notice instead of lambda, here we have an alpha. Now, if I find the first and second derivatives, I end up with an acceleration vector x double prime equal to constant alpha squared v e to the alpha t. So notice we just made a copy of the e times the constant vector v times the derivative of the exponent 2 times over, so we end up with an alpha squared here. We want to substitute this into the matrix equation, and from that we will derive our characteristic equation. So plugging this into our matrix equation, x double prime, I'm going to write sub here, x double prime is alpha squared times vector v e to the alpha t equal to matrix A times x. Remember, x was v e to the alpha t. Notice we can divide both sides by e to the alpha t because it's never equal to 0, and we end up with alpha squared v equals a times v. Let's subtract the vector alpha squared v from both sides. When we do, that's going to leave behind the 0 vector, not just 0, but a 0 vector. This is equal to AV minus alpha squared v. Being careful to factor preserving the order of multiplication of those matrices. We're going to factor out the eigenvector v. Notice here I'm going to put a placeholder identity matrix there. So we end up with matrix equation 0 vector equals a minus alpha squared I. Remember, this makes this defined operation. A is a matrix, alpha squared is a constant, so in order for that subtraction to be defined, we have to multiply alpha squared by an appropriately sized identity matrix. As we saw in the last equation, it's going to look like alpha squareds along the diagonal times vector v. Now, the characteristic equation then is derived from this result. This matrix equation will have a non-trivial solution provided the determinant of the coefficient matrix is non-zero. So the characteristic equation is then determinant of a minus alpha squared I equal to 0. So I'm going to solve this characteristic equation for alpha squared. We're going to use that to find the eigenvalues and the eigenvectors. Notice the difference here is we have an alpha squared as opposed to a lambda in the previous section. So let's associate this with what we already know. Typical eigenvalues are negative real numbers. Thus, our previous eigenvalue, lambda, is now in the place of alpha squared. That's going to be some sort of negative real number. So when we solve for alpha and we take the square root of both sides, we're going to end up with some sort of positive and negative constant times I. Omega is going to be the frequency of the system related to our eigenvalues lambda. Now, let's put this all together and write a general solution for the system. So, Theorem 1 from this section of the text, for distinct eigenvalues, lambda sub 1, lambda sub 2, up to lambda sub n, those are going to be alpha squareds. We can simplify them as negative omega sub 1 squared, negative omega sub 2 squared, so on and so forth, with associated eigenvectors v sub 1, v sub 2 up to v sub n. The general solution of x double prime equal to ax is given by x of t equals, notice here we've applied Euler's formula. We have a 0 real part for our solution, so e to the 0 t becomes 1, times a sub 1 cosine of omega t, there's the imaginary part of our solution to the eigenvalues, plus b sub 1 sine of omega t. So that looks like it did in Unit 2 with a single differential equation. Now to update it for a system, we're going to multiply by these associated eigenvectors v, so that this gives me not just a single solution, but a system of solutions. Let's try an example. Example 1 and our last example for the semester. Find the natural modes of oscillation for a 3-spring, 2-mass system with m sub 1 equals m sub 2 equals 1, spring constant k sub 1 equals 4, and spring constant k sub 2 equals 1. Hang on, guys, I have some typos here. Let's correct this. K sub 1 is going to be 1. K sub 2, I'll sneak it in over here, is going to be 4. And K sub 3 equals 1. We should have 3 spring constants because we have 3 springs. Now, notice this situation right here. Our masses are both 1. We're only going to consider this option because remember up here, in order to, when we set up our mass matrix, in order to solve the system, we were required to find the inverse of that mass matrix. If we have 1s along the diagonal for our mass matrix, then M inverse is an identity matrix. So an identity matrix is its own inverse. Because we don't have a lot of experience with finding the inverse of a matrix, again, this is the only possibility that we're going to consider. If we have different masses, we are required to find the inverse of a matrix, and we haven't yet learned how to do that. So we're going to keep this a simple, focused application. Let's go ahead and set up our system. Equation number 1, we're going to have mass m sub 1 times x double prime. M sub 1 is 1 times x sub 1 double prime equals, now keep an eye up here on our stiffness matrix, and we're only going to be using a 2x2 form of this. So entry number 1, that is row 1, column 1, is negative K1 plus K2. So if I add K1 and K2 for this problem and find the negative, we're going to get coefficient negative 5 for x sub 1. Okay, let's look at the second entry in our stiffness matrix. Second entry here is K sub 2. So for our particular problem, K sub 2 is 4, so we get 4 times x sub 2. Working on our second equation, we have x sub 2 double prime. Let's take a peek at our stiffness matrix. Again, ours is a 2x2 system. The next entry is going to be K sub 2, so the same as what I had previously. That's going to be 4 times x sub 1. And then our last entry that we need to consider, negative K2 plus K3. So the sum of K2 and K3 is going to be 5, and we need to negate that. So the good news is our particular application is one spring, one mass less than our general solution. So we have two equations in two unknowns. This is a second order system. So our goal is to write this in matrix form and determine our characteristic equation. So in matrix form, we're going to have mass matrix 1, 0, 0, 1 times acceleration vector x1 and x2 double prime equals stiffness matrix -5, 4, 4, and -5 times displacement vector x sub 1 and x sub 2. As I mentioned before, because our mass matrix is an identity matrix, we can write our system without that matrix, and we don't have to worry about finding an inverse to a matrix. So our matrix A for this particular problem is the same as our stiffness matrix. We need to determine our characteristic equation. As we did in the previous section, we have the determinant of A minus lambda times I equal to 0. Now, the lambda is going to be related to an alpha squared. We will point that out here in a minute. So we need to find the determinant of matrix A, what we have right here, minus lambda times I. We learned previously that feels like subtracting the eigenvalue, lambda, along the diagonal. So calculating this determinant, we have our forward diagonal product, -5 minus lambda times -5 minus lambda, minus the reverse diagonal product, 4 times 4. Foiling here, we have 25 plus 10 lambda plus lambda squared minus 16 equals 0. And rearranging, we have lambda squared plus 10 lambda plus 9 equals 0. When we factor, we have lambda plus 1 times lambda plus 9 equals 0. Thus, we have two distinct negative eigenvalues. Lambda sub 1 equals -1 and lambda sub 2 equals -9. These are the values that I'll use to determine the eigenvectors, but remember in the development of the problem, we made an association between the lambdas and alpha squared. So let's make that observation at this point. If lambda sub 1 equals -1, then alpha squared equals -1. We're going to take the square root of both sides. Oops, not alpha 2, alpha squared. We're going to take the square root of both sides, and we'll call this omega 1 equals plus or minus I. So I'm just saying the square root of alpha squared gives me omega 1. Then our second eigenvalue, lambda sub 2, coordinates with some alpha squared. And taking the square root of both sides here, we get plus or minus 3i. So I'm going to use the eigenvalues to determine the eigenvectors. These are going to be expressed in the natural modes of oscillation for the system. So let's put in the work to find our corresponding eigenvectors. So let's begin and find eigenvector v sub 1 corresponding to our first eigenvalue, lambda sub 1 equals -1. Now, remember, the way that we do this is going to be the same as it was in our previous section. We're going to use our eigenvalue -1, and we're going to plug it into our matrix A minus lambda I multiplied by V equal to 0. So we are using the form A minus lambda I times vector V equal to 0 vector to determine our eigenvector. So A minus lambda I, again, is up here, and we're going to plug -1 in for lambda. So in position 1, we have -5 minus -1. That's going to give me a -4. And then we have a 4 here. Then we have 4, and -5 minus -1 gives me another -4, times eigenvector v sub 1 with components v1 and v2 equal to 0 vector. Now remember, this is a dependent system, so both equations that come out of this system are going to look the same. So multiplying row 1 times column 1, we end up with the equation negative 4v1 plus 4v2 equals 0. And notice, if I derived the second equation, we'd have 4v1 minus 4v2 equals 0. In either case, we're going to end up with the same relationship, v1 equals v2. So solve for v1 in terms of v2 in both equations, you end up with v1 equals v2. So let's make an easy choice. Let's suppose that v2 equals 1, then v1 would also equal 1. Thus, we can say eigenvector v sub 1 equals 1, 1. So our first solution, x sub 1 of t, is going to be equal to e to the 0t times, let's call it a sub 1 cosine of t plus b sub 1 sine of t, b sub 1 sine of t, times eigenvector v sub 1, which is 1, 1. Okay, so notice this part is reminiscent of what we did in chapter 2 when we have an imaginary root to our characteristic equation. The real part goes in the exponent with e. The imaginary coefficient is the coefficient of the argument on our trig functions. Okay, let's repeat that again and find our second eigenvector. I'm going to come up here for a little more space. Let's find eigenvector v sub 2 corresponding to our second eigenvalue, which was negative 9. So again, we're looking at the matrix equation A minus lambda I times vector V equals 0 vector. So we're going to plug this time negative 9 in for our lambdas. Over here, there's A minus lambda I. Negative 5 minus negative 9 gives us a positive 4 in both of these two spots, times our second eigenvector, v sub 1 and v sub 2, equal to 0, 0. If we translate this back into equation form, both equations are going to look the same. And if we solve for v sub 1 in terms of v sub 2, this time we would end up with the opposite value. So if we choose a particular value for v sub 2, we're just going to have the opposite value for v sub 1. So let's suppose that v sub 1, and this is our second eigenvector, let's suppose that v sub 2 is equal to 1, then v sub 1 would be negative 1. Thus, our second particular solution, x sub 2 of t, is going to be e to the 0t, again 0 is the real part of this number, times a sub 1 cosine 3t, 3 comes from the imaginary coefficient, plus b, let's make that sub 2, b sub 2 sine of 3t times eigenvector negative 1 and 1. So we have two natural modes of oscillation. Those are identified by our omegas. Let's make a few observations for this particular problem. The two natural modes of oscillation occur at frequencies of omega sub 1 equal to 1 and omega sub 2 equal to 3. Looking at the natural frequency omega sub 1 equals 1, which came from this particular solution, notice that the amplitudes of our sine and cosine would be the same, okay? And our period there would be 2 pi. So at frequency omega sub 1 equal to 1, the period of oscillation would be 2 pi, and the masses would oscillate in the same direction. That's because we've got the same sign for each term of our first eigenvector. Looking at our second frequency, at frequency omega sub 2 equal to 3, the period of oscillation would be 2 pi over 3. And the masses would oscillate in, notice the opposite signs of the terms of our eigenvector, they would oscillate in opposite directions. So in one natural mode of oscillation, the masses are going in the same direction, and at another natural mode of oscillation, the masses would oscillate in opposite directions. And all of that could be obtained by looking at the frequency and our eigenvectors. Now, this is a very simple system, but it can be applied to such situations as, let's suppose that you have railway cars that are attached by rigid springs that oscillate naturally relative to those springs. You could model the effect of compression or extension of those springs between railway cars. In a similar way, this can also be applied to a vertical system where you're looking at the relationship between floors in a multi-story building and how those floors oscillate relative to each other. Specifically, how would they behave in an earthquake? So you can use a very simple system such as this, and the more information you have, the stronger the need for a computer algebra system to manage all of that information. But now you have the knowledge for a basic setup. So that completes our notes for differential equations. Congratulations for making it this far. Thank you so much for your hard work. You've got one more homework assignment to complete and just a few more hoops to jump through before the end of the semester. So thank you again for your hard work and have a great day.